Hello everyone, and welcome back. Today we're going to continue our exploration of single variable calculus and begin the formal study of what calculus actually is. One of the most common ways in the modern day of studying the foundations of a calculus course is typically from the perspective of limits. Now, I'm going to introduce limits from the formal definition, which you may or may not encounter in your elementary calculus class. But I do want to introduce it so that you do know that this is not just some hand-wavy type of mathematics that isn't really formally defined. And of course, we'll go into the conceptual and the graphical and the numerical calculations of limits just to make sure that we have a more well-rounded presentation of what a limit actually is before we get into the more serious concepts of a single variable calculus series. So, what is a limit? So we say that the limit as x approaches a, so that's how we read this first statement. So the limit as x approaches a of the function f of x, and we say that the limit of a function is equal to some number L, and it could be a negative, positive, zero, or irrational, rational number, doesn't really matter, if for every epsilon that is positive, and typically epsilon is going to be an arbitrarily small but positive number, there exists an associated delta that typically depends on epsilon that is also greater than or equal to 0, such that if the difference between x and a is arbitrarily small, in particular less than delta, then the distance between f of x and L will also be arbitrarily small as well, and in particular will be less than the associated positive number, epsilon. So when we ask, what is the limit of a function, since by this definition we're sort of comparing the x values and the a, which definitely should belong to the domain of that function f, then L typically is going to be associated to the range or is going to be compared to the range of the function of interest. So for every epsilon, there exists a delta. So it's sort of like a game, right? So what they're going to do is they're going to choose a particular epsilon, and then you're going to choose a particular number delta that depends on that number epsilon. Let's get a little graph going to sort of get a conceptual understanding of what's actually going on here. So what I'm going to do is I'm going to graph a very basic function to start off with. Let's assume we have the function f of x, which is going to be equal to 2x minus 1, which is just a basic line. So let's assume, obviously, that this function is defined on all the real numbers, which we can choose to be. And let's consider what's going on to the function when x is getting close to 3. So notice that we can get close to 3 from either the left or the right directions. So what is happening to the y values as x is getting closer and closer to 3? Well, obviously they're going to be approaching that blue dot, right? So as x gets closer and closer to 3 from either direction, what is happening to the associated y values? They should be getting closer and closer to some number, either from the bottom or the top directions associated to how the function is changing on its associated domain. So again, somebody's going to be choosing an epsilon. So epsilon is going to be an arbitrarily small but positive number. So let's assume that this corresponds to L plus epsilon, and this corresponds to L minus epsilon. Obviously, there's going to be some associated x values that are corresponding to those projections. So we're going to have this point here and that point there. So they choose an epsilon, and we should be able to choose a delta that sort of controls or surrounds this element in the domain 3 based upon this precision that is based on this number of epsilon for which was chosen. So this obviously is going to be 3 minus delta and 3 plus delta. So regardless of this epsilon that sort of is surrounding this L number, which is to be defined, hopefully we should be able to find a delta that sort of surrounds this little 3. So the closer and closer, the smaller and smaller that epsilon is, then obviously the smaller and smaller this delta is going to be, and you should see that this box, in some sense, is going to sort of close around that particular point and sort of squeeze in that point. So does this curve have that unique point for which it approaches? Well, in this case, it looks like it's going to get closer and closer to f of 3, which we know is going to be 2 times 3 minus 1, which is 6 minus 1, which is going to be 5. So a nice conjecture at least would say, well, as x gets closer and closer to 3, and that obviously is from all directions, and in the two-dimensional domain case, or the one-dimensional case, we can only approach 3 from the left and the right, so the left and the right. We clearly see that f of x appears to get closer and closer to 5. So if that is the case, then we will write the limit as x approaches 3 of this function, and again, this means from all possible directions, not just the left, not just the right, but all possible directions, we will say that this is equal to 5, regardless of direction. So let's see if we can present a nice little proof for this particular example, right? So what are we trying to do? So we're trying to show that the absolute value of f of x minus L is less than epsilon, whichever epsilon they have chosen, right? So f of x, we know, is going to be equal to 2x minus 1, and the proposed L value is 5, right? So if that truly is the limit, then we should be able to conduct this proof, right? And again, our goal is to show that this distance is less than whatever epsilon for which they have chosen. So if we do a little bit of algebra here, notice we have minus 1 minus 5, which is going to be minus 6. And we can factor out that 2 there, so we have 2 times the absolute value of x minus 3. And since that 2 is a positive number, we can factor that out, so we have 2 times the absolute value of x minus 3. Now keep in mind that the domain value for which we're focusing on is 3, right? So in the definition, this is our x minus a, which should be less than delta, right? So if that's going to be less than delta, then this is going to be less than 2 times delta. Now we need to show that this is less than epsilon, right? So what value of delta do we need to choose in order for that to be true, right? So what we can choose is we can choose delta to be equal to epsilon over 2. That's not the only value that will make this work, but it will work in this case. So we're going to have 2 times epsilon divided by 2. And that's obviously just going to be epsilon. So we have that this is less than epsilon, which completes the proof. So let's sort of conclude what we've shown here. So that means for any epsilon greater than 0, there exists a positive number delta also greater than 0. And in this particular case, one can choose whatever epsilon value they choose, just divide that by 2. So if they choose 10, you're going to choose 10 divided by 2, which is going to be 5. So it's always going to work for this function, such that as long as the distance between x and 3 is less than delta, which is chosen to be epsilon over 2, then we're always going to have that f of x minus this number 5 will be less than epsilon. Therefore, we conclude that the limit as x approaches 3 of the function is equal to 5 for this particular function. That's how we formally will conduct a limit proof, but for elementary calculus courses, we do not usually go this formal. So let's go through a little bit more of a graphical and intuitive way of calculating limits via both graphs and also algebraic approximations. So let's start off with a basic rational function with x squared minus 5x plus 6 on the top and x minus 2 on the bottom. Clearly, since this is a rational function, the only issue for this function is when the denominator is equal to 0. So we should be able to clearly see the domain of this function is going to be the set of all real numbers except for positive 2, since that's going to generate a division by 0 issue. Therefore, we will write that g of 2 does not exist. Now, just because the function does not exist at that point does not imply that the limit at that point does not exist. If we perform some algebraic manipulations on this function, notice that we can factor the top, in particular into x minus 3 times x minus 2 divided by x minus 2, and we clearly see that these x minus 2's will cancel. But keep in mind this is only true for x is not equal to 2, And notice that we're just left with x minus 3. So in terms of the graph of this function g, the graph practically looks like the curve x minus 3, except we have a hole at x is equal to 2. So if we give this a graph, and just do a quick sketch of it. So 1, 2, 3, there. So this is going to be the graph, and one can find that, okay, well, if this is x minus 3, then that's also going to be equal to 3. So when x is equal to positive 2, there should be a hole there. A hole. Hole with an H. Right, so technically, there shouldn't be a line through there. And it should look something like that. Okay, because g of 2 is not defined. So, if this is the graph, what is the limit as x approaches 2 would be the question, right? So it appears to be that as x gets close to 2 from the left and right, this curve does appear to get closer and closer to some number, in particular whatever y value is associated to that hole, right? So one could conjecture from this graph that maybe approximately go to -1, maybe -2, or something like that. So we can claim that the limit as x approaches 2 of g of x may be equal to whatever this curve is getting close to, right? And that would obviously be 2 minus 3, which is going to be equal to -1. And indeed, you would be right. Right? So if you happen to have this issue because you can't divide by 0, which occurs when you have 2, so this x minus 2 factor is the issue, if you're able to remove that issue that is causing that singularity in your domain, then on occasions you can substitute the value for which is not in that domain in the first place, causing that issues, into whatever function is it transforms into when you cancel out that particular domain. So yes, g of x is not equal to x minus 3 in the typical sense because x minus 3 is defined on all real numbers because you cannot technically plug 2 into this function because g of 2 is not defined, right? But this function on its own, we can call it, for example, f of x, has the same exact graph without the hole, right? And we want to know what is going on around 2, therefore the limit of this function and the limit of g has the same exact limit values since that issue is easily removed, right? There are some formal ways to sort of present that from the delta-epsilon definition, but we of course save that for a more elementary, say, real analysis discussion, which we'll save until a little bit later. So the limit is a y value that the function gets close to as the x domain values get closer and closer to the domain point or lack thereof domain point of interest regardless of the direction. Now, I keep on emphasizing this regardless of direction thing. So let's look at an example where direction actually makes a difference. So let's consider the sine function, SGNX, and in case you don't know what this function is defined to be the function, the absolute value of x divided by x for x is not equal to 0, and 0 for x is equal to 0. So if we take a look at what this function looks like, and you can do a table of values in case you're not comfortable with it, would sort of look like this function. So it has y is equal to 1 on the right, y is equal to -1 on the left, and then y is equal to 0 at the origin. Okay? So, what is going on in this picture? So obviously this function does not have any issues. Obviously the only point of interest would probably be at x is equal to 0, right? For example, if I say what is the limit as x approaches -3 of h of x, well, -3 is going to be over here, and it looks like it's approaching -1 regardless of direction. So we would say -1 for that limit. Let's see, let's just erase that. So it goes to -1. Now if I say what is the limit as x approaches 5 of h of x, well, 5 would be somewhere over there, and it appears to be approaching 1 regardless of direction over there, so that would be equal to +1. But if you look at 0, notice that we approach -1 from the left and positive 1 from the right. So we can write that in this way. So the limit as x approaches 0 with a minus sign, so that's 0 from the left-hand side. We see that that's equal to minus 1. And if we're interested in the right-hand side, notice the limit as x approaches 0 plus sign, that's the limit as x approaches 0 from the right-hand side. We see that this function is getting close to positive 1. Now, again, this should be getting closer and closer to the same point regardless of the direction, but we clearly see that the two possible directions you can approach 0 from on the real line is just left and right, and we obviously get two different values. Obviously, these two different values are not equal to each other. Therefore, since they are not equal, when they say the limit as x approaches 0 of h of x, what does this mean? This is the limit regardless of direction. It should be a unique number, but it's not. So in this case, when the left and the right-hand limits do not equal to each other, they're equal to either different numbers or they themselves do not exist, then we say that the limit does not exist because it's not approaching a unique value. So let's consider this third example, where f is defined to be the function e to the x minus 1, all divided by 5x. Obviously, we see that the domain of this function is going to be all real numbers except for the value for which generates 0 in the denominator, which is still going to be 0. So that's the domain. So if somebody asks you what is the limit as x approaches 0 of f of x, you cannot say that this is f of 0 because f of 0 is not defined. So what is it? So if you're a beginner to limits, sometimes a safe place to start is just to look at the graph and sort of see what is going on to this function as x gets close to 0 from both directions. So if you were to graph this curve, then you would get a graph that is similar to this. So it appears to look similar to the exponential function e to the x, something like that. But it obviously is going to have this hole there. But even though this function does have a hole at x is equal to 0, the y values still appear to approach the same value from both sides. So whatever y value that is will be the limit of this curve, at least from the graph. So if it is a unique number, then it shouldn't matter which value I approach this point from, either from the right or the left. So let's do a couple numerical approximations, because notice f of 0 is the only point that's not defined on this curve. I can plug in any other point into this function because it's defined at all x except for 0. So how would I approximate the limit as x approaches 0 from the left-hand side? And when I say the left-hand side, that means I'm going to pick a number, for example, here, and then I'm going to pick a point here, and then I'm going to pick a point here. And I'm just going to get closer and closer and closer to 0, but not touch it. And I'm going to see if my y values appear to be getting closer and closer to something. So here's my x values, and here's my associated f of x values. So obviously you can be a little bit flexible with these points. So for example, we could choose negative 0.1, negative 0.01, and negative 0.0001, for example. And let's just look at these y values. So if you plug this into your calculator, we get something approximately equal to 0.1903. And for that one, you're going to get 0.1990. And then for this, you're going to get 0.199999, and so on. So, okay, well, that's pretty interesting. So what is going on, for example, on the other side? So the limit as x approaches 0 from the right-hand side. So obviously I'm going to pick a point here, and then I'm going to pick a point closer on the right, and then I'll pick a point closer on the right, and see if the y values appear to be getting closer and closer to something. So let's sort of see what that looks like. So I'm going to pick a number slightly bigger than 0, so 0.1 is a good number, 0.01, and say 0.123 and 1, right? So almost like a mirror image, I guess you could say. So for the f of x values you can find, that's approximately equal to 2.103, 0.2010, and 0.2123 and 1, right? So do these y values appear to be getting closer and closer to something? Possibly you can conjecture that the limit as x approaches 0 from the left is approximately equal to 0.2, and the limit as x approaches 0 from the right of f of x, although we don't know it's exactly equal to 0.2, we can definitely say it's approximately equal to 0.2. And since these are equal, then we can say, since those are the only two directions we can approach 0 from, we can say that the overall limit is approximately equal to 0.2, or as a fraction, 1 divided by 5. Right? Now, again, this is just a conjecture, but one can show later on with some more advanced tools that this is indeed the true value, right? So the limit as x approaches 0 f of x is equal to 1/5, but still keep in mind f of 0 does not exist, right? So just because the function does not exist does not necessarily imply that the limit does not exist, and also vice versa. Let's consider another function example, and let's introduce sine into the conversation just in case maybe you forgot what sine looks like. So you should know that the sine is a periodic function and has sort of like a wave-like structure to it. And obviously, since we're dividing by x, obviously we have some domain issues to clarify. Obviously, the domain of g is going to be all real numbers except for 0, because the top sine of 2 plus x, that's always between -1 and 1, regardless of the x value. And then we're just going to be shifting that down by a sine 2 value. So we're just going to be sort of having a shifted, slightly modified version of the sine function. And one should be able to show that the graph of this sort of has this type of pattern. So if we take this sketch as relatively accurate, and x is not equal to 0, and if this is truly drawn to scale, then notice that the y values again appear to be getting closer and closer to something as x approaches 0 from the both left and the right hand side. So if you do not know how to evaluate the exact value, we could always use approximations to sort of get a feel for what's going on there, just for approximation purposes only though. So let's do the same as before. So for the limit, as x approaches 0 from the left-hand side of this function, what are we going to do? Well, we're going to pick numbers that are close to 0, but on the left-hand side. So for example, -0.01, -1, 2, 3, and 1, and then -1, 2, 3, 4, 5, and 1. So I'm getting a little bit more precise than I did with the last example, just because this function may appear to be a little bit more odd than before. And if you use your calculator, you're going to have that that's approximately equal to -0.41159, -0.41610, and -0.41615 approximately. And then I'm going to do the same for the right-hand side. So the limit as x approaches 0 from the right-hand side. Choose some x values, and then find the associated y values. So I'm going to choose positive 0.01, and then 0.0001, and then 0.123451. And then I'm going to plug in some values. So you're going to have -0.42069, and then -0.41619, and -0.41615. So we see that as x approaches 0 from the left and the right, that the values appear to be getting closer and closer to something, which is definitely a good sign. Now, obviously, if you get closer and closer and closer and they start to get farther and farther away, that's definitely something that should concern you, and you should look at the graph to sort of see if that makes sense. So we can say that the limit as x approaches 0 from the left and the limit as x approaches 0 from the right are both approximately equal to -0.4161, and you can find more decimals if you want, in particular 468, and so on. So since the left and the right are the only directions for which you can approach 0 on the real line, then we can say that the limit as x approaches 0 from all possible directions will also be approximately equal to negative 0.41611468, which one can find with some more advanced techniques is actually just equal to the cosine of 2, which may not be obvious to see why that is the case, but eventually you'll find out. Let's assume that somebody gives you the graph of some arbitrary function and asks you to find a bunch of things about it. For example, let's assume that we have this graph here, and let's assume that the name of this function is f. So what if somebody asks you, what is f of 3 equal to? So f of 3, in case you do not remember, is where the closed dot is along the line x is equal to 3. And notice that the closed dot is located at a y value of minus 4. Therefore, f of 3 is going to be equal to minus 4. Now let's calculate the left hand, right hand, and the overall limits of this function at x is equal to 3 and sort of see what they are equal to. So the limit as x approaches 3 from the left is equal to what? So as we approach 3 from the left-hand side, we're going to be approaching a y value of 5, right? So we say that the limit as x approaches 3 from the left will be equal to 5. Now let's consider things from the right-hand side. So as we approach 3 from the right-hand side, we're going to be coming down this slope and approaching a y value of minus 2. So we say that this limit is equal to minus 2. And again, those are all the possible directions. So since the left hand and the right hand limits are not equal to each other, then we will say that the overall limit as x approaches 3 of the function does not exist because the left hand and the right hand are equal. And keep in mind, evaluating limits is independent of the functional definition there, right? So f of 3 could have been equal to 5, negative 2, or non-existent at all, but that does not influence the value for which the limit can take. Notice that for all these examples, up to this point, we've been looking at limits as x approaches finite numbers, but you can also approach infinite numbers even though you never get close or exactly to them. So let's look at a particular example. In particular, the limit as x approaches positive infinity of 5 divided by x squared plus 7x plus 1. So keep in mind, we're substituting an arbitrarily large but positive number into this rational function, right? And you should know that this rational function is practically dominated by this x squared term, because as x gets arbitrarily large, the 7x plus 1 term becomes practically irrelevant. So the limit will be the same in both of these cases, so we can say that this is actually precisely equal to the limit as x approaches positive infinity of 5 divided by x squared. And we should know that this graph sort of has this type of shape, and we know that this actually goes to 0 as x gets close to positive and also negative infinity. Now, some people will try a bit of an algebraic style to this problem. So for example, we can consider the limit as x approaches positive infinity of, again, 5 over x squared plus 7x plus 1. And what they'll do is actually divide top and bottom by x squared. So when you do that, you're going to have the limit as x approaches positive infinity of 5 divided by x squared all over x squared divided by x squared, and then plus 7x divided by x squared, and then 1 over x squared. And then we're going to have that's just going to be left with the limit as x approaches infinity of 5 over x squared all over 1 plus 7 over x plus 1 over x squared. Right? And if you substitute infinity into these functions, which are all elementary, with 7 over x looking sort of like that curve, notice that that's going to be equal to 0 all over 1 plus 0, which is 0 divided by 1, which is 0, which is, of course, the same exact answer. So there are some conceptual things you can use, but of course you should use caution when you're sort of new to limits, that you can use for especially rational functions. Let's look at a couple other examples just to make sure we get it. So let's assume that we have the limit as x approaches positive infinity of x squared plus 5x plus 2 all over x plus 1. So obviously as x gets arbitrarily large, x squared is the dominant term of the top and x is the dominant term of the bottom. Or you can divide top and bottom by x squared and you'll get the same answer as you will get here. So that's obviously going to be equal to the limit as positive x goes to positive infinity of, and we're going to have, for example, x squared divided by x. So x squared divided by x, which is going to be equal to the limit as x approaches positive infinity of just x. But what does that curve look like? So y is equal to x looks like this curve, and as x gets arbitrarily large, this gets arbitrarily large and goes to infinity too. So some people will say that the limit is equal to positive infinity. Some people will also write D and E for does not exist or is not finite simultaneously. So make sure, at least in terms of conversational purposes, you know who you're talking to and what they expect you to say when you encounter a limit that goes to an infinite quantity and not a finite one. So let's look at another example also. So the limit as x goes to positive infinity of 3x squared plus 2x plus 1 all over 5x squared minus 3x plus 2. So using the same realm of logic as the last couple of examples, we have the limit as x approaches positive infinity of 3x squared will be the dominant of the top and 5x squared will be the dominant of the bottom. So the x squareds will cancel and we're left with the limit as x approaches positive infinity of 3 divided by 5. And we know 3 divided by 5 is just a constant function and is always equal to 3 over 5, regardless of the value that you're approaching, and hence that is your curve. Now, in case you don't know the significance of these limits at infinity, one can say that y is equal to 3/5 is the horizontal asymptote of this associated rational function. So you remember back when we studied rational functions in depth back in foundational mathematics, you do know that rational functions have both vertical and horizontal asymptotes, and one now has a more formal tool of finding horizontal asymptotes via limits as x goes to plus or minus infinity. So let's take one other example of infinite limits to sort of see if you understand the main idea. So what is the limit as x approaches negative infinity of e to the positive x plus 2 divided by x plus 5? All right, so let's analyze each of these functions independently. So e to the x we know has that shape, 2 over x has that shape, 5, that shape. So as x goes to minus infinity, we know that e to the x has a horizontal asymptote of 0. As 2 over x goes, as x goes to minus infinity for 2 over x, that goes to 0 as well. And 5 always stays 5 at negative infinity in particular. So this is going to be equal to 0 plus 0 plus 5, which is equal to 5. So if you have some rigorous understanding and comfortability with your graphs of your elementary functions, some limits are actually quite easy and quite trivial to figure out what they actually should be equal to. There are some limits that actually are quite special, but are actually quite difficult to prove for the elementary audience. So what I want to do is just list some special elements out, just in case you're in like a calculus course that is not very rigorous or theoretical based, or maybe you just want to have some limits to do other things that you want to engineer or solve applications with. So I'm just going to list these functions out and their associated limits, so you're at least aware of them. Some courses will just say memorize these, some will say prove if you're super clever, but I just want to list them out and prove them later once we have the maturity to do so. So the first limit I want to look at is the limit as x approaches 0 of the function sine x over x. And for all of these functions, you actually should be able to generate a graph and actually figure out what they should be equal to. So I'm just going to list these limits out, and maybe you can figure out them on your own. So sine x over x is 1, cosine of x minus 1 divided by x is another. The limit as x approaches 0 of e to the x minus 1 over x is another. The limit as x approaches 0 of the natural log of x plus 1 divided by x is another. And another one would be the limit as x approaches plus or minus infinity of 1 plus 1 over x to the power of x, right? So you can possibly use a graph, pause this video, and see what numerically they should be approximately equal to. But one can find formally that this is equal to 1, this is equal to 0, this is equal to 1, this is equal to 1, and this is equal to e, where e is approximately equal to 2.71828, and so on. So there's some special limits. There's definitely infinitely many of them aside from these five, but these are the common five that you definitely need to know about in an elementary treatment of single variable calculus. The last thing I want to mention in terms of this introduction to limits is what is referred to as indeterminate forms. Indeterminate forms are forms of limit evaluations that you get when you substitute, but they don't really tell you anything useful, i.e., you cannot figure out what the limit is, i.e., it cannot be determined, hence the name indeterminate. So if you plug in a number into the potential domain of the function, for example, sine x over x, for example, which we know gets closer and closer to 1 as x gets closer and closer to 0. But sine of x gets closer to 0 and x gets closer to 0. So we say that, sine of x over x gets closer and closer to the indeterminate form 0 divided by 0. And we know that 0 divided by 0 doesn't exist. Therefore, we have to do some clever tricks to sort of figure out that it's actually equal to 1, right? So every time you see these forms, for example, 0 divided by 0, 0 divided by infinity, 0 times infinity, which is not 0 and not infinity, infinity minus infinity, which is not generally 0 or not generally infinity, 0 divided by 0 to the power of 0, which is not always equal to 1 or not always equal to 0, 1 to the infinity, which is at least trivially, some people say, well, that's always equal to 1. Not necessarily true, because if that's the case, then that means 1 plus 1 over x to the power of x, because 1 over x goes to 0 as x goes to infinity, and we're having 1 to the power of infinity. So we're like, oh, that should be equal to 1, but we know that that actually gets closer to e, right? And of course, infinity to the power of 0 will not always be equal to infinity and will not always be equal to 1. So every time you see these things, don't try to assign a number to them because it's likely that you're going to be making a mistake. So in any of these forms, when you start substituting the limit point of interest into that functional representation f of x, and you get these expressions, which we call, again, indeterminate forms, then you cannot directly figure out what the limit is, and you have to manipulate the function to get a form that is not listed above. Now, although theoretically you can manipulate the function, sometimes it's not obvious at all. So what I want to do is just close this video with an example of sort of some of the clever tricks that you would have to come up with if you were to truly manipulate this function. So let's consider the limit as x approaches positive infinity of the function the square root of x plus 5 minus the square root of x. So if we sort of substitute the positive infinity into these functions, because we know that the square root of function and its horizontal shifts always go to positive infinity, so this, via substitution, is infinity over infinity, which is one of the indeterminate forms. Therefore, this has no meaning to us. So is it possible that we can perform some algebraic manipulations on this function to sort of get something a little bit more meaningful? And indeed you can. So one trick that is commonly used algebraically for radicals when you're adding and subtraction, and also complex numbers have the same exact trick, is multiplying top and bottom of this fraction by the conjugate of that numerator. So in this case, the conjugate would be the square root of x plus 5 plus the square root of x, and the bottom would also be the square root of x plus 5 plus the square root of x. So on the top, the structure has this form a minus b times a plus b, which we know is just a squared minus b squared. So those radicals will just cancel, in particular equal to x plus 5 minus x, right? Which is just going to be equal to 5. So this is going to reduce down to the limit as x approaches positive infinity of 5 all over the square root of x plus 5 plus the square root of x, right? Now notice that the top is constant, and we know that infinity plus infinity, an arbitrarily large plus an arbitrarily large number, is also arbitrarily large, right? In particular, we can say that this is practically equal to the limit, as x approaches positive infinity, of 5 divided by, because 5 is not significant, so this is the same as the square root of x plus the square root of x, which is just the same as the limit as x approaches positive infinity of 5 over 2 square root of x, right? And we know that this 5 divided by the square root of x function is practically like the 5 over x function, except it's not defined on the negative side of the world, right? And we know that this goes to 0 as x gets close to infinity, and hence this infinity minus infinity happen to be equal to 0 in this case. I wouldn't say it's equal to, but it sort of transforms into 0. Right, but obviously the algebraic tricks in order to make that sort of come out and become obvious actually what it is equal to, sometimes not at all obvious and definitely requires some practice or memorization or prior exposure or a combination thereof. So those are some of the fundamentals associated to limits, which we're definitely going to use here and there throughout the series, but there's definitely other little tricks for which are commonly applied to limits, which we'll introduce when the time is appropriate. So I hope you enjoyed this video, and I'll see you in the next one. Take care.